Hi everyone, in this video we are going to go over integrated rate laws. There are two forms of rate laws that we study when we talk about kinetics. And so actually let's back up a step. So remember, kinetics is the study of the fact that reactions most often take a period of time to occur. Most of the reactions we study first semester go very quickly, but in reality most reactions, things like drug metabolism in your body, or just digestion, take place over a period of time, and we need some way to measure that and quantify it. And we try to do that through something called rate laws, and there's two kinds of rate laws. There are integrated, which is what we're going to talk about in this video, and then there's differential rate laws. If you've had calculus, you might recognize these terms. If you haven't, don't worry about it. The key thing is that integrated rate laws are going to involve time, and differential rate laws are going to involve rate, all right? So under the integrated, we could also put concentration in there as well, all right? So time and concentration are going to be found in integrated rate laws. Rate and concentration in a different way are found in differential rate laws, which I'm going to show you in just a moment. Both of them are going to share a constant called the rate law constant, K, which is lowercase k. We're going to call that the rate law constant. And that's going to be in common between integrated and differential rate laws. Okay, so let's look at what these look like. So the problem is, and what makes this hard for most folks, is that there's more than one possible set of rate laws that govern a reaction. Well, how do you know? Well, you do an experiment and you see which one fits, basically. And I'll show you I'll talk through how to do that in just a moment and give you a moment to practice it as well. In general, there are three possibilities of sets of rate laws. And when I say a set of rate laws, I mean both differential and integrated. And in general, there are three possibilities. We label them with numbers, 0, 1, and 2, and we call that number the order. This is not first, second, and third. It is just a dumb name for a number that pops up in the equations as I'm about to show you. When you look at the differential rate laws, as I said earlier, they all involve rate, and they all involve the rate constant. And then you plug in the concentration here. Remember, the brackets mean concentration in moles per liter. And then you plug in as an exponent the order. In other words, this number here, the order, becomes the exponent over here in the differential rate law. All right? So in the first order reactions, you have an exponent here of 1. In the second order reactions, you have an exponent here of 2. Right? Depending on the year and my mood, I cover these in different orders, so we may have talked extensively at this point about differential, and we may not have, and that's okay. Again, the focus here is the integrated rate laws, which I've written over here on the right-hand side. So the 0 order, the 0, 1, and 2 do not appear in the integrated rate laws. You just have to know that they go together. So for 0 order, the integrated rate law is concentration. Again, remember the brackets mean concentration in moles per liter. All right. The concentration is equal to minus, and then there's that rate law constant that we saw is also in the differential rate laws, times time plus, now what this symbol over here means, this is the initial concentration. So in other words, it's the concentration at time equals 0. That's why there's a little subscript 0 here. It's a subscript, it's just a label. It's not an exponent or anything like that. You don't do anything with it, it's just a label. So so you would read this whole equation here as concentration of A equals negative rate law constant times time plus initial concentration. All right? I know it's a lot of symbols, so you'll get used to it. All right, in the first order reactions, we have the appearance of the natural log function, and some of you may or may not be super familiar with this, depending on how far you got in your Algebra 2 textbook in high school. And if you're not super familiar with it, don't worry about it too much. There's a button on your calculator that'll do this for you. We'll talk more conceptually about logarithms when we get to acids and bases. It's a lot easier to do the base 10 ones in your head. This is a logarithm of base E. Again, we'll cover it at a later point. All right. So for now, if you're not super sure what that means, again, We're just going to use the numbers on our calculator or in Excel, however you calculate it. Okay, anyway, we would read this equation as the natural log of the concentration is equal to negative KT plus the, oops, I left out a naught, plus the natural log of the initial concentration. Right? And then in this last one down here, we're going to have the inverse of concentration, so 1 over the concentration. I'm a lot of times going to call it inverse. The inverse of the concentration is equal to KT plus 1 over the inverse, or sorry, 1 over the initial concentration, or the inverse of the initial concentration. Okay, so those are the rate laws. So what does all that mean? Well, the goal here is to figure out which set applies. Is a reaction 0 order? Is it first order? Is it second order? The way we do that is we kind of go in reverse. Instead of starting with the equation, we start with the data and we figure out which equation is the one that matches the data, and then that tells us which rate law to use. So you have to, if you're trying to determine the order, you have to make 3 graphs. Only one of those 3 graphs will be linear, and that's the one you're looking for. So if the concentration versus time is linear, then the reaction is 0 order, right? Because that fits the rate law that we saw up here, concentration versus time, all right? And that would be in the form of y equals mx plus b, that's a straight line. If that's the one that comes out to be a straight line, the reaction is 0 order. If the natural log of concentration versus time is a straight line, then the reaction is first order. If 1 over the concentration versus time is linear, then it's second order. What you'll find is that only one of these will be linear and the other 2 will be curves. So you'll have to make all 3 graphs each time, but only one of them will actually be a straight line. And then you can ignore the other 2 once you know which one is the straight line, but you always have to do the experiment. Okay? You'll get a chance to do this in lab at some point, but we're going to do a pencil paper example here in just a moment. The key thing here that's really handy experimentally is that the slope of whatever your linear graph is equal to the rate law constant. Technically, it's the negative of the slope for these first 2 because, actually, I want to write that the other way around. I want to write k equals negative m. So k equals negative slope, all right? And this came up, I think, in the previous video briefly about slopes and negatives, and it's not super important. If you do this for a product, it's an increasing line. You don't need to worry about that right now. Anyway, I'm rambling. Okay, so the key thing here is that the slope of this line is going to be the rate law constant, and that's going to be super helpful because that gives us all the numbers we need to plug into the rate law and use it. Okay, so not only does making all 3 graphs tell us what the order is it 0, is it first, is it second order, it also gives us the rate law constant by finding the slope of the line. Okay, I'm going to give you a practice problem because the only way to do this is to kind of slog through it. So I've written up a practice problem here. I want you to determine the order of this reaction. I've already made 2 of the graphs for you. One of them is the one you need. Determine the order of the reaction and find the value and units, which we haven't really discussed, but we'll go over in this example, of the rate law constant k. All right, so I've given you 2 graphs here. It's a little hard to see on this graph because I had some trouble with the whatever. But there's a point right here, and it lies on the concentration axis, and this is a time axis down here. This is a natural log of concentration axis, and this is a time axis down here. Okay, so I couldn't get my graph to have labels on it because I was being computer challenged. Anyway, first figure out what the order is. Is it 0 first? And I haven't given you the second option, so it's really just 0 or first order. Then figure out the value of k. Okay, go ahead and pause the video. Try to work on this for a few minutes. If you get stuck, just restart the video and I'll go through it. All right, hopefully you've had a chance to at least muddle through a little bit. Notice that this one on the left here is a curve, right? So if we, and I did that badly, but it's a curve. It is not a straight line. Whereas the one on the right-hand side is a straight line. I'll connect it with dashed lines because I can do those better. Okay, that's a straight line. So that tells you right away that this reaction is first order. Okay, so the equation that's going to apply is ln, oops, what am I doing? ln of a equals negative kt plus ln of a naught. Okay, so that gives us the differential rate, the integrated rate law. It also gives us the differential rate law, by the way, because that means that rate will equal k times a to the first, because that order, whatever the order is, just goes there as the exponent in the differential. Okay, now we got to find the value of k. So how do we do that? Well, we need to find the slope of the line, and we've done this a number of times in some other contexts. So we just need to take any 2 points, all right? I'm going to take this point, and I'm going to call it 0, negative, I don't know, 0.7-ish. And I'm going to take this point over here, and I'm going to call that 5, minus 3.2. All right? And then I know that slope is equal to delta y over delta x. Your high school teachers may have said rise over run for that. That's fine too, if that rings a bell. y2 minus y1 over x2 minus x1. So x1, y1, x2, y2. I always make you should always make x2, y2 the ordered pair to the right, further to the right. All right. So now y2 is negative 3.2 minus y1, which is negative 0.7. And we're going to divide that by 5 minus 0. Okay? So m, which is going to be k, or, here. Let's do this systematically, Stephen. Come on. All right. M is going to be equal to, get out my calculator, negative 3.2 minus a negative 0.7 is plus 0.7. So that's negative 2.5 over 5. That I can do in my head. That's minus 0.5. Now, remember from earlier, the slope and the k are negative of each other, so k equals negative of m, so that's going to be positive 0.5. You could also think of this as k equals the absolute value of m. I'm really not fussed either way. Some people get super stressed about this, but anyway. Okay, so let's think about units now, which we didn't really do earlier, and I didn't warn you about. So notice that the y-axis here we're told is unitless. Anytime you take the natural log of something, it makes the units go away for mathy reasons that, again, we'll get into at some later date. So we have no units in our numerator up here. We have minutes down here in the denominator. Right? So our number is, when we calculate this down here, we've got no unit over minutes, no unit over minutes, and then, so we're going to end up with minutes. I like to move this up to the numerator and call this minutes to the negative 1. All right? So, yeah, that's how I prefer to do that. Okay? If that bothers you, you can do it however you like, but some people write 0.5 over per minute, and I think it's goofy. I think it's just easier to move everything up to the numerator. Okay? All right. That's how you do these. It is just a matter of recognizing which graph is linear. That one's linear. And then doing the same algebra techniques we used for tangent lines to find the slope. All right? Okay. I hope this was helpful. Please leave a comment if you have questions, or just get in touch. All right. Thanks for watching.